Okay, I think we are good to go. Sorry for being late, there was some network issue in the institute. Okay, let us start. Okay, let us begin. So, welcome you all to the week 11 problem solving session for the NPTEL course titled Multirate-DSP. Myself, Saurashis Chatterjee, a PhD scholar from IIT Kanpur, and in this session I am going to solve a few problems based on the contents of lecture of week 11. So before jumping to problems, today's problem nature is mostly going to be theoretical. Of course there will be 2 or 3 numerical problems, but most it's theoretical because week 11 lectures deal with analysis of WebDM in greater details. Of course it has been analyzed in previous lecture also, but in this particular lecture what we have seen is okay. System is creating a bit problem here, so let me just check the issue. Just a minute. Sorry for the interruption. System got kind of hanged. Giving it a minute to resolve. Guess need to close some tabs. I think it won't be a problem anymore. Okay. Thing might be uh, shutting down my video might help here, otherwise it will keep getting hanged only. So just let me check with that option. Okay, I guess it worked. Fine. We can continue. Sorry for the interruption. Okay. So where are we? Yeah. So week 11 lecture. We are just briefly discussing here what have been covered in lecture 11. Okay. So OFDM details, then we have seen circulant matrices are been introduced in previous lectures also, and we have, I guess we have covered it in part in previous session. However, in today's session we are going to look into its structure in more details. So circular matrices and its properties, namely circular shift, just a minute. Diagonalizability, etc. We'll also see pseudo-circular matrices and its properties. We have seen previously its structure and all. I think there are few problems which will deal with those. And in today's session there is a numerical problem which focuses on the okay, we'll see that in the problem itself. So let us start solving our problems here. So first question asks that which is following is going to be true for a circular matrix. What is the first option is first column may be arbitrary. That questions our knowledge about circular matrix, that whether it's going to have some impose a specific structure over the elements of column or not. Second one considers the columns other than the first are circularly shifted. Third is always diagonalizable, and fourth is all of the above are true for a circular matrix. See, in previous session we have considered the idea of pseudo-circular matrix, and while covering it we just briefly discussed what circular matrix is going to be. Circular matrix, as its name suggests, first of all it is going to have some circular property in some sense. First of all, that is correct. And now if we go into the details of a circular matrix, what happens if you see from a row perspective or column perspective. Let us consider first from perspective of columns. So what is going to happen if you have pick a random column from a circular matrix? The column preceding it, I mean the next column, is going to be a circularly shifted version of previous column by 1 unit, where the shift is downwards. That is, if you know one column of a circular matrix, you can easily have other columns also, because the elements remain same. It's just that the preceding column has been shifted downwards 1 unit compared to previous column. And why the shift is fine, we understand the shift part, but why we call it a circular shift or the name circular matrix? Because the last element of a column goes to the first element of its preceding column, I mean the next column. That is, it kind of follows a circular trajectory, where the last the last element comes out to be the first one when you move to one column to another. Similarly, if you see from the row perspective, it's just that if you uh, choose any of the row of a circular matrix, you go to the next row, and this row is a shifted version, circularly shifted version of previous its preceding row by 1 unit to the right. Here also the last element of a row comes out to be the first element of its next row. So both row and column perspective, you have this circular shift property, where the column it happens downwards, and for rows it happens on the right. So yeah, that is it. And the columns have identical elements only. Yes, their order are changed, but if you have information about any column of circular matrix, you can easily uh, derive the other columns by just circularly shifting them in the particular order. And same applies for rows also. Okay, so okay, without wasting time, let us first give you an example of circular uh, circular matrix. Here I denote it as C, which has the following structure. And by the way, it's always going to be a square matrix, where first element is C0, second is C1. Similarly, up to, you are going to see up to element Cm minus 1. So the next column, as we have discussed, you look at the previous column and you shift the element of the previous column downwards by 1 unit. So your C0 is coming to this position here. Similarly, C1 is going to be here. Up to that, we also talked about the last element. So last element, let me denote with different color here. So this Cm minus 1 is the last element of the first column. We call it circular matrix because it follows the circular shift, which is nothing but it follows this trajectory. Please don't take this drawing as it face value. I'm just showing that if you move to one column to the next, it is going to happen. This Cm minus 1 is going to come here, and here you end up with Cm minus 2, and this goes on for row and column wise. At the end, what you are going to get is, you can already assume what the element is going to be here. If we follow the row structure, the C1 is the first element of the next row, so therefore C1 must be here, the last element, which follows a circular shift in this manner. Let me show you here. Yep, so it is going to follow this manner, and it is going to come at the first position of the next row. And the elements of columns and rows remain identical only, I mean across the columns and across the row, not across these rows and columns, not that. And they follow this particular order only. C1, C2 up to C0 is going to be here. Also interesting property you can observe for the circulant matrices, if you consider along the principal diagonal, you see the elements are going to be C0 only, and similarly across this diagonal C1 is all going to be C1. But these are, you see, these are the descending diagonals from left to right. When you are moving from left to right, these are the descending diagonals. In contrast, if we look towards ascending diagonals, the property doesn't hold. Let me add one more element here, C2, then things will become more clearer. C2. Okay, so if you look along this ascending diagonal, you see the elements are not going to be same. It's C1, it's Cm minus 1 here. You see the next ascending diagonal, it's C2, C0, Cm minus 2. So according along the ascending diagonals, these properties are not going to hold, but along the descending diagonals, the elements are going to be same, and this property hold for both the circulant and pseudo-circulant matrices, which will come later. So this is a circulant matrix, and this is always going to be a square one. So let us see these conditions one by one. The first statement is first column may be arbitrary. So if you see the first column, we do not impose any particular structure on those elements up to C0 to Cm minus 1. They can be anything, right? So we are not imposing a particular structure or some conditions they have to follow, or there are some correlation between these elements, nothing of that sort. They are denoted as C0 up to Cm minus 1, and they can be absolutely anything. It's like all the elements can be different, one extreme, on another extreme up C0 to C minus 1, all can be same, it doesn't matter. So therefore the first property, so let me write it here, properties of C, we see there is no particular structure or condition over the elements of first column of these elements can be completely arbitrary. So the first property hold. Next we need to check the next property, that it says the columns other than the first are circularly shifted. So to check that, let us move to our next column. This is the first column, let us denote it. So first we move to second column, and what we observe, second column is the circularly shifted version of the first column, but the shift is downwards by 1 unit. So let us write it down here. Second column is the circularly shifted version of the first column where the shift is downwards by 1 unit. If you see that from the perspective of row, it remains the circularly shift property holds true when you move from one row to another. It's just the shift direction changes when across the columns, when the shift is downward by 1 unit. Across the rows, the next row is the circularly shifted version of previous row, but the shift is in the direction of right. I mean, when you move to left to right 1 unit. That is the property. So this statement here we make about second column. It can be generalized as follows, that jth column is the circularly shifted version of j plus 1th. Oh, sorry, I should have, it's j minus 1, it's the preceding column, sorry about that. And this hold for all j, varies from 1 up to m, or you can consider to 0 up to m minus 1. It's the matter of index only. And in the lectures we have also seen, it's important that this C satisfied the diagonalization property. So let me write down here first, then I will break it down and explain a little bit. We have seen that C, the circular matrix C, it satisfies the diagonalization property. I will explain in a minute what this is. I guess we have seen in that lectures also, but it's a good thing to review again. Okay, so we've seen in lectures that the matrix C can be equivalently written in this format: W Hermitian capital gamma W. In lecture the notation is also used as a underline, so let us be according to that put it, easy to understand. Where is Hermitian, of course, refers to the transpose conjugate. I guess you are familiar with that. The matrix W is the normalized DFT matrix that makes W Hermitian, the IDFT, because W being Hermitian. Okay, but by the way, W is a Hermitian matrix also. That means W Hermitian is going to be equal to W inverse only. So let me write down these small properties here, otherwise it's difficult to remember. So first thing is W is normal. I will explain in a minute the structure of W itself. Normalized DFT matrix W is also Hermitian. Satisfying the following property, that is your W Hermitian is equal to W inverse. So let me here mention how you structure this matrix W here. The k mth elements of W, this is the k mth element, kth row and mth column, is given as follows. Of course, we say it's a normalized DFT matrix, so there should be a square root of m term before, where Wm is equal to mth root of unity, whose expression we are well aware of, e to the power minus j 2 pi over m. So this is the structure of W. Next we are concerned about this capital gamma, which is by the way, these all are m cross m square matrices. This normalized DFT matrix and IDFT matrices, and this gamma, of course it's a diagonal matrix, so it must be a square only. Gamma 0, gamma 1, gamma 2 up to gamma m minus 1. This is a diagonal matrix of size m cross m, and there is also one important relation exists between these elements of gamma capital gamma, that is denoted as gamma naught, gamma 1, gamma 2, and this W normalized DFT matrices. I mean the not exactly W, it's the element of C, which is given as C naught up to Cm minus 1. That is, this gamma m's are the DFT of the elements of this circulant matrix C. That is, the elements of the circulant matrix are C naught, C1 up to Cm minus 1, and gamma m you can obtain by taking the DFT of these elements. So let me write it down. Gamma m's can be obtained. The writing pad is again creating some issues. Let me just check once. I guess the system is still hanging a little bit. Let me just check once. Okay. If I turn on the camera, okay, it is going to heat a lot, so it won't be possible. Okay, we continue as it is. Video cannot be turned on, I guess. Okay, we are discussing the, just a minute. Okay, I guess the meeting is still on. Okay, turn it off. Guess this is fine, and okay, the recording is on, so things are fine till now. Okay, so we are discussing the interrelation between the elements of this diagonal matrix capital gamma and the elements of the circulant matrix C. So therefore you can obtain this gamma naught up to gamma n minus 1 can be obtained by computing DFT of any column of this matrix C. Of by computing DFT of the, you can say, first column of or any column of the matrices, because anyways if you know the elements of one column you know the other columns also, because the elements remain identical across columns. First column of C as follows, that is you obtain delta m taking these coefficients which is Ck, and multiplying with the suitable weights Km, sorry, not Kn, Km it should be. Anyway, I'm not changing the eraser because system is creating some problem today. K runs from 0 to m minus 1. So this is the relation between the elements of this diagonal matrix gamma and the constituent matrix elements along with C. So therefore we have seen that this is true, this is true, this is also true. Therefore your first the fourth option is going to be correct only. So the key takeaway from this discussion is that if you find out one of the conditions true and you have the option that encompass that, I mean for this example, for this problem it's all of the above, so you need to check the other statements also whether they holds true or not, because it's objective type question and you know that you read the first statement, that first column may be arbitrary and you found it to be correct, and you take the first option, then it's going to be wrong only. So you have to check the other statements in sequence and check whether they hold true or not. Then only you proceed to choose the correct option. So with that, let us move to our second question, which regarding said that the communication system has following attributes. You have number of subcarriers 124. So basically it's a FDM system where you break down your wideband channel into narrowband subcarriers, and the modulation scheme, you have a bunch of choices to take from, that is BPSK, binary phase shift keying, where you can transmit either -1 or 1, so therefore you have 2 bits only. So number of bits per symbol we have seen in earlier sessions is log base 2m, where m is the number of bits per symbol. It's sorry, number of bits in constellation, and log base 2m gives us the number of bits per symbol you can transmit. So for BPSK there are only two symbols in the constellation, -1 to 1, sorry, -1 and 1 to choose from. So therefore m is 2, therefore the number of bits per symbol is going to be log base 2m, which is 1. So for BPSK you can transmit 1 bit per symbol, and that's quite obvious also intuitively. For QPSK, however, you have 4 options, 4 symbols to choose from. The constellation constitutes of 4 symbols, namely 0 0 0 1 1 0 and 1 1. So since you have 4 symbols to choose from, your constellation size is 4. Therefore number of bits per sample you can transmit is log base 2m, which is log base 24, that comes out to be 2. So for QPSK you can transmit 2 bits per symbol. For 16 QAM your constellation size is 16, so therefore you can transmit log base 216, that is 4. So using 16 QAM you can transmit 4 bits per symbol. Similarly, using 64 QAM you can transmit log base 264, that is 6 bits per symbol. Using 256 QAM you can transmit log base 2 to 56, that is 8 bits per symbol. And of course at the end you have 1024 QAM, that is you are allowed to transmit log base 2024, that is 10 bits per symbol. Remember one important thing: when you move to a higher modulation scheme, that is from BPSK to QPSK, QPSK to 16 QAM, 16 QAM to 256 QAM, and many more, you must see that number of bits per symbol you can transmit increase. So on a higher level, without getting into much technical details, you can understand that you can transmit more number of bits per symbol. Therefore your achievable throughput is going to be high, and that is true only. But to be able to use this higher modulation scheme, you must have proportional SNR. For example, your SNR is poor and you are willing to transmit, you are asking your transmitter to transmit using modulation scheme of 1024 QAM, it is not going to be possible, because for example for 1024 QAM, which is a pretty high modulation scheme, you receiver should have very good SNR to be able to decode it properly. Why I am saying, I am just giving a hint, maybe I'll elaborate on it in a little bit in details in a later slides, that when you have a fixed constellation space, and for PPSK that constellation space consists of only 2 symbols, whereas for 16 QAM the same constellation space constitutes of 16 symbols. So what happens from BPSK to QPSK, the relative differences between adjacent symbols become pretty less. For example, I am giving you this example here. BPSK, you have a constellation scheme, we have two elements as -1 and 1. However, when you move to QPSK, what you are going to have, you have this 0 0 1 0 0 1 1 1. Just a minute. So if you draw a circle like that for BPSK and QPSK both, it is going to be like this only. So for QPSK, let me point it down here, where this crosses the position of symbols. So yeah, it's like that. So for BPSK, you see the difference between the symbols. In case of QPSK, it's already reduced. We are considering the same radius of these two circles in case of BPSK and QPSK to make the constellation size same only. So what is going to happen? This difference between two symbols A1, and here the difference between those two symbols, adjacent symbols of course, A2, you can see clearly that A1 is greater than A2. And similarly, when for like 16 QAM or 64 QAM, you are encapsulating more symbols inside the same constellation space, what is going to happen? The mutual difference between these symbols become less, and that means it has become harder to decode. That is why the probability of error is going to be high. And from Shannon capacity theorem, we have seen the you can always transmit data with arbitrarily low probability of error if it's less than or equal to channel capacity, and that is a function of SNR. So for a particular SNR, the bit error probability is higher for higher modulation scheme. So in some sense, you can consider the lower modulation scheme may have achieved a lower throughput, but they are more robust, because since their symbols are situated quite far away from each other, they give you the luxury, or they give a higher margin to improve your decoding performance compared to the scenario when your symbols are pretty close to each other. Then decoding becomes very difficult unless you have very high SNR, because your noise is going to disrupt your symbol position, and the probability of mistaking one symbol for another is going to be quite high, because for higher modulation scheme you don't have this margin between these two symbols if you visualize them in constellation space. For example, in 8 QPSK you might have a symbol here, and a little bit of noise, and this position of this symbol can at receiver will see this position only, so receiver will falsely decode is as this one, but the original symbol transmitted is this. Whereas BPSK, the probability is less because it is going to take a lot of noise to falsely, the receiver to falsely decode this symbol as this one. So that is the main reason of introducing the redundancy, or yeah, this forward error correction, that is rate 1 by 2. What does rate 1 by 2 means? That for every message bit you are sending one redundant bit. To the entire goal is to make it robust. You cannot send the bits in a naked manner. Mostly what happens, you do some error correction coding on that. Basically means you add some redundant bits or parity bits or zero padding or whatever you do. You just code it into some robust data stream compared to your original data stream, which is going to be negate the effect of fading channel or noise to certain effect. That is the goal. Okay, we'll come to that later. Enough of this discussion. Then we have seen that forward error correction codes we are available is like this, and duration of one WebDM symbol is 15 microsecond, and bandwidth expansion ratio is 14 by 30. This is an important term also, bandwidth expansion ratio. What does it mean? You consider a block of data, basically data in practice in wireless transmission, data is communicated via blocks of data. So if one block, there is a data length is m, so there your usually block length is greater than that, that is n. Suppose you have m symbols in a particular block to transmit, and you introduce some gamma symbols for 0 as cyclic prefix, parity bits, zero padding, whatever your ways of introducing redundancy or robustness, then your block length become of size n, which is more than m. But you cannot, so your bandwidth gets expanded. So we'll come to that mathematical formulation, but you must see that the redundant bit doesn't carry any information, I mean any actual data information. Your data bits is m only, that goes into the bandwidth being used to carry this data. This additional, when you introduce this redundancy, it is going to expand your bandwidth. That bandwidth you need to transmit this amount of data, which is data plus redundant data, the end product of this operation. So that expands your bandwidth you need to transmit. So that is bandwidth expansion ratio. Let me draw give you an idea of bit error probability. I am plotting here bit error probability, and if it's a semi-log scale, like you start from 1, of course, that is 10 to the power 0, and see 10 to the power minus 1, 10 to the power minus 2, 10 to the power minus 3, and in here you have SNR in dB scale, SNR in dB scale. Maybe like you start from let's say 0, it's minus 5 here, that's 5, it's 10, 10, 20, and it goes on like that. So therefore your modulation schemes are going to have a performance quite like that. This doesn't follow always what I am drawing, but this is usually the case. So I am drawing 3 cases, not to make things too much complex for you, but I hope you'll get the idea from it only. Draw another. And this one. Okay, let me point it out one by one. So this one here is the BPSK. BPSK. This one you consider to be a 16 these are like the arbitrary curve. In that sense, I may not have their position right in the correctly or the BR values, but the shape is more or less same, and it is to give an idea of how things are. And this the last one is suppose 256 square. So you can say for any particular SNR point you choose that is represents a vertical line, your BPSK is going to have the lowest bit error probability, simply because it has the maximum difference between the symbols in constellation. That gives your decoder the best margin or the best probability to correctly decode your data. Whereas you move towards higher and higher modulation scheme, and you are incorporating higher number of symbols in the same space, the mutual difference between the symbols decreases. That means a slight addition of noise here and there, and there is a very high probability that the receiver will falsely decode a symbol as some symbol which is different from what is being transmitted, which causes the bit error probability, which actually being translated into nothing but non-zero bit error probability. So you take any SNR point, you will see that BPSK is going to have the best bit error probability. Whereas you can see for higher modulation scheme, like this for 256 QAM, to achieve a reliable bit error probability, maybe like 10 to the power minus 2, you can consider that they are achieving almost around this. If I see 10 to the power minus 2 to be a more or less decent reliability, that is only 1 out of 100 bits are going to be error, which is not of course very good in today's standard, but still can somehow reliable. It is going to achieve at SNR of 20 at this high SNR, whereas this BPSK can achieve it around 5 or 6 dB. You can see the difference. Of course, that is only because this large difference between the symbols is going to provide your decoder and receiver a bigger margin to correctly decode whatever being transmitted. Of course, it is going to result into low throughput, but it is more robust in that sense. So robust corresponds to the case where you have this uh, reliability is very high, that is your bit error probability is less. That is what robust is. So in the question asked what is the minimum throughput of the above system. So minimum throughput we have already understood from this curve that modulation scheme is going to be BPSK only. Now it comes to forward error correction code. Now for that I draw the following plot here, again an arbitrary plot, so please don't get into the values, rather if you understand the concepts, that's good enough. So the axis remains same only. Of 10 to the power 0, 10 to the power 1, sorry 10 to the power minus 1, it is semi-log scale across the y-axis. Here you have 10 to the power minus 2, here you have 10 to the minus 3, like that. And this plot I am going to draw is, for example, fixing a modulation scheme. Let us fix the BPSK. Okay, let us draw the SNR here. Here the SNR is bit more uh, flexible, maybe minus 5, minus 3, minus 1, 1, 3, 5. More granular, in the sense we are introducing this. Sorry. Yeah. So let me introduce what are these actually. So here this corresponds to a code rate of 5 by 6. It's a pretty high code rate. That's 0.833. Of course, that means every 5 data bits you are adding one redundancy bit, making the whole length 6. This one corresponds to a code rate of 3 by 4. That means every 3 data bit you are adding 1. And here the code rate we are fixing to be 1 by 2. That is for every data bit you are adding one redundancy bit. And we have seen the bit error probability is going to be least. That is, the system is going to be most robust when the code rate is minimum. And in an intuitive way you can also understand that, as I will explain now. Let's see what is happening. First of all, you take the example of this repetition code. Repetition code is nothing but, suppose you have 1 0 to transmit. What you do, you do not care about your resources, that you say that you want the, you can tolerate lower throughput. That's not the issue. The data rate is not your primary concern, the reliability is your primary concern. So what happened, you are transmitting 3 zeros instead of 1 0. Like 1 0 is your data bit to be transmitted. You transmit 2 additional zeros, 2 redundant information, and along with that, so that corresponds to a code rate of 1/3, correct? Because you have one data bit, that is 0, you send additional 2 zeros, making the total as a 3. So it's a 1 by 3. The different way of writing, you say your code rate is 1/3, or another way of writing is 3 comma 1 code. That's the same way of writing things. That's not the issue. The thing is, when you compare the cases on the naked transmission, that is you are transmitting your data bit only, which corresponds to code rate of 1, that is you are transmitting 0, and the case when you are transmitting 3 zeros. In case of first instances, if you are transmitting 1 0, and if some channel condition and noise is going to flip your data, that is 0 is received decoded, falsely decoded as 1 at the receiver, then what happens, your bit is decoded incorrectly, that is there is an error. Whereas you send when 3 zeros, and suppose the same thing, your 1 bit got flipped, what do you receive? You receive 0 0 1, correct? 1 bit got flipped. Now in this case, according to majority decoding rule, the receiver will simply say that which is the dominating symbol in this block length of 3 of this bit. It will see 2 zeros, 1 1, so it is going to rule in the favor of 0. It will say okay, 0 is being transmitted. So therefore your data, you can consider your data bit is decoded in a proper manner, or the probability, error probability is 0 now. So both first and second case you can similar, but you can see when you are doing a naked transmission, you are having your bit error probability, your bit being decoded erroneously, and the second case the same thing happening, your noise or channel is going to flip one bit of information, but still the other two bits are that doesn't have nothing happened to them, they are decoded as they is 0. So therefore you are able to decode the bit correctly. So introducing the redundancy saves you, correct, in the sense that you are able to achieve reliable communication. Of course you need to spend additional resources, your redundancy is pretty high, that is fine, but you are at least able to achieve reliable communication. That's the whole point of introducing redundancy. So we can see from that example that lower the code rate, more robust your transmission scheme is going to be, because lower code rate means you are introducing more and more redundancy in maybe of different formats, maybe just repetition code, maybe zero padding, you or achieve you cyclic prefix or something like that. But whatever way you are introducing redundancy, you are making whatever you are transmitting your data bits more robust to the channel failure. That is, even if your channel, like for this example I have given you now, they're transmitting 3 zeros, even if for one of these bits get flipped by poor channel condition, the rest of the 2 bits are received as it is. Therefore according to majority decoding rule, receiver is going to uh, uh, give the verdict in favor of zeros. Therefore it will be able to understand that okay, 0 is being transmitted. So even if your one bit goes into failure, is decoded improperly, you are still able to correctly predict or correctly decode the data which is being transmitted from transmitter side. So that reduces the bit error probability. So when I say the most robust scheme, it's basically a combination of the modulation scheme you are using and also the forward error correction code rate you are using. So you should pick the lowest modulation scheme and the lowest forward error correction code rate, which gives you the maximum margin to beat the channel uncertainty in order to achieve reliable communication. So when I say sorry, just a minute, it is again hanging. I just don't understand the reason why it is behaving in such manner. guess we can get back to our discussion. And yeah, where are we? Okay, the minimum throughput corresponding to, write it down here, minimum minimum throughput corresponding to most robust scheme can be achieved for this question using the lowest modulation scheme and lowest FEC code rate, lowest modulation scheme and lowest FEC code rate, which correspond to highest reliability. So the throughput calculation is pretty much easy, so let me just write it down. Oh, before that, let me explain the bandwidth expansion ratio. This is 14 by 13. I would like to write them in context of whatever notation is used in lecture, so you are better able to understand. Where this M is the number of data bits and gamma is the number of redundant bits. So introducing these redundant bits in your data stream is going to expand your bandwidth that you need to transmit the naked data stream. That is, suppose you need bandwidth of B to transmit your naked data stream. Now because of introduction of this redundant bits, your this bandwidth, for example, suppose become a scalar a times b, where a is a fraction more, sorry, a is not a fraction, a is something more than 1, maybe for example 1.01 or 1.02, something like that. That's why we call it bandwidth expansion ratio. You need more bandwidth compared to when you transmit the naked data stream, or corresponds to when you are using some error correction coding before transmission. That is the difference. So throughput, for calculation of throughput, you first consider number of subcarriers, because each of them are going to contribute in this entire throughput calculation. Now whatever you are writing, holds for one subcarrier, like for each subcarrier. First of all, your number of bits per symbol, number of bits, so let me write it down properly. Number of bits per subcarrier symbol. Since the throughput is calculated in bits per second, you must divide that with duration of one symbol, duration of one OFDM symbol, and that is without cyclic prefix. And we need to introduce with the inverse of bandwidth expansion ratio. Why? Because we don't need, when we calculating throughput, that corresponds to whatever throughput you are achieved by transmitting your data. Your redundancy bit calculation doesn't comes into picture for that. You understand what I am saying? You transmit your processed data stream which involved some coding, some redundancy bits using some bandwidth, but that bandwidth doesn't correspond to your actual data transmission. Your actual data transmission bandwidth is lesser than that, a fraction of that, which is the inverse of bandwidth expansion ratio. So we need to multiply with 1 over bandwidth, sorry, expansion ratio. Okay, so here we are taking the product of 124 number of bits for BPSK. We have seen this corresponds to your modulation scheme. Oh, I forgot to introduce the code rate myself. Sorry about that. Code rate is introduced to take into account the amount of redundant information, you see it from other perspective. Code rate here is introduced to find the fraction of original data in whatever you are transmitting. That is for code rate of 1 by 2. Out of every 2 bit, your 1 bit is your data and 1 bit corresponds to redundancy. So you are only using 50% of your bits is actually your data bits. So since throughput corresponds to only your data bits, it has no it is not concerned about whatever redundant bit you are sending, because they are not considered as information. They are just to protect the other half of it, that is the data bits you are transmitting. Therefore throughput calculation, you must consider the code rate to take into the fraction of data among the whole stream being transmitted. So it's 1024. Number of bits for BPSK is log base 2 base 2, because constellation only consists of 2 symbols, therefore it comes out to be 1. And duration of OFDM symbol is 15 microseconds, so therefore it's 15 to 10 to the power minus 6 into 1 over bandwidth expansion ratio, which is 13 by 14, a fraction, and then comes out to be half. So it's like 124 into 13 divided by 15 into 14 into 2 Mbps. I just took this 10 to the power minus 6, absorb it, so it's become Mbps. And after calculating, let me check. 1024 times 13 divided by 15 divided by 14 divided by 2. Okay, it comes out to be, if I approximate 2 decimal, 31.70 Mbps. Okay, so the minimum throughput for the above system comes out to be 31 Mbps, 31.70 Mbps. Okay, now on the opposite extreme, this third question asks what is the maximum throughput we can achieve from the above system. Similarly, when you say the maximum throughput, in minimum throughput with most robust scheme corresponds to your goal is different there. Your goal is you do not concerned with the throughput is your least concern. You are focusing entirely on the robustness. Your entire goal is to increase reliability, so you are sacrificing throughput there for reliability or to achieve more robustness. Here when you are saying about maximum throughput, your goal is completely changed. You are trying to extract as much data as possible. Reliability is not your concern here. So for maximum throughput, you are going to choose the highest modulation scheme, and I need not say it why we are to choose highest modulation scheme, because highest modulation scheme or a higher modulation scheme are capable of transmitting more number of bits per symbol, that is directly proportional to your throughput. That's why we are going to use the highest modulation scheme to achieve maximum throughput. And also you cannot spend much on redundancy, so you are going to choose the highest possible code rate you are available. For our example, the highest possible code rate is 5/6. So main idea is that you see from this point of view that you are not willing to spend anything over redundancy bit. Just your system is constant, you need to use a forward error correction coding, so therefore you are choosing the maximum code rate which corresponds to the minimal redundancy. So let me write it down here. We are going to choose maximum code rate, and when you say maximum code rate, it is nothing but minimum redundancy. So see, from the compared to previous question, the goal is completely changed. Now we are want to achieve maximum throughput, and we will do whatever it takes to do that. So to, of course, to maximize your throughput, you need to increase the proportion of data in the coded stream. So that can be only achieved if you minimize the redundancy and maximize the amount of data. That is, you are going to maximize the code rate, which corresponds to minimum redundancy. Correct? So our choice of modulation scheme is going to be 124 QAM, since this is maximum available for this given communication system here. And F is E code rate here, this is 5/6. Correct? So your maximum throughput is going to be number of subcarriers into code rate. This remains same only if I just copy from previous one also. Number of bits per subcarrier symbol. So its throughput is in terms of bits per second, so you must divide that with the duration of symbol, and you should take into account the bandwidth expansion ratio. So number of subcarrier is 124, the code rate is going to be 5/6, the number of bits is going to be, let me write it down for your understanding. I haven't written it for BPSK, but QAM I guess it might help. And 15 into 10 to the power minus 6 into 13/40. The two things that have changed compared to previous computation is the code rate and the number of bits per symbol. The rest of the terms remain same only, so it's like this. Log base 2024 comes out to be 10 to 13 divided by 6 into 15 times 14 Mbps. Similarly, I have absorbed the 10 to the power 6 into calculation, and it comes out to be, let me check once, 1024 into 50 into 13 divided by 14 divided by 15 divided by 6. Oh, it comes out to be 528.25. Therefore our answer is going to be 528.25 Mbps. This one is the correct. Let me check whether I have done for previous thing. Okay, I have not written it. It's 31 points. So only difference in throughput calculation in maximum and minimum is going to affect your code rate and the modulation scheme, which directly reflects into this quantity, the number of bits you are sending per subcarrier symbol. So these two are only your concerns. With that, let us move to our fourth question here. Now fourth question says that you have two statements and you have to find whether they are true and false and all their possible combination. So we have seen the zero forcing equalizer in lecture. Equalizer, as the name suggests, what it does, it just equalize. In what sense? Let me just tell you. It equalize in the sense that it tries to your channel, when you pass through a channel, consider the Z transform of channel to be CZ. So channel, from a signal processing framework, you can consider perform some action over your transmitted signal. And what equalizer do is going to invert, or what should be the good word, it just tries to nullify the impact of channel. That is, whatever the channel do, it just try to do the opposite, with the goal to achieve the transmitted signal in its original value. Of course, for that you need to have the complete idea of the CZ, the channel structure, which is very difficult to obtain in wireless communication, but more or less the goal is that you want to equalize in that sense. Whatever the channel has done to your transmitted sequence, you are going to undo it. That's the goal. And what zero forcing equalizer do that? Very simple, it just invert it. So in terms of Z transform, you pass through a LTI system, your output, what you are going to, if you consider channel to be a filter only, mimics is the LTI filter, you have XZ, you transmit through this channel CZ, you are getting at output yz, which is cz time xz. Of course you are not taking into account, you are considering it memoryless, that is the there is no block interference, one block is not going to interference with its previous or next block. You are making your communication robust, we are ignoring that fact, but the goal is that, so therefore your output is yz is going to be xz times cz, and in output you at receiver you are employing this zero forcing equalizer 1 over cz, which is undoing the effect channel have over the transmitted signal. So ideally 1 over cz and cz are going to cancel each other, so you are going to obtain xz whatever being transmitted at receiver as yz in an intact form. Of course that's the ideal case, that's the goal with which you proceed, but you may not achieve it because you always don't have the correct expression of cz all the time, and all this memoryless or LTI property doesn't hold, so that also introduces error. Those are different things, but yeah, that is the case. And it says that zero forcing equalizer is likely to introduce noise. Okay, I think the term here is wrong here, written is correctly, it should be enhancement, not environment. I guess it got some typo here, it should be likely to introduce noise enhancement, and this happens when channel have very small gain. Okay, in practicality when you say that channel, like ideally the channel gain can be 0, but what happens due to presence some noise, some delta, the cz has a very small value lambda z. So when you are going to equalize it, that is 1 over cz, you can see it 1 over delta is going to be very high because delta is very low, and that is going to amplify your noise, and that problem exists with zero forcing equalizer. So both these statements are true. So let us just see mathematically what exactly happening. So you have this input signal here, input signal that passes through some processing by, I means this number of, like FDM concepts you have seen the number of channels, you are combining them, taking the DFT and this redundancy you are incorporating, you are basically coding your data stream, and all that I am considering as to be some kind of black box here, because those are not our concern in this question, considering it's black box, and that is being transmitted from transmitter. We are considering this channel to be this is channel with z transform cz, and we are going to receive output signal yz, and here you are transmitting xz, so everything is fine. Your yz is going to be xz times cz, and if you employ equalizer ez, which is given as 1 over cz on yz, then your y dash z, that you obtain by combining ez with yz, is going to be 1 over cz times xz times cz, and they basically cancel out, and this is the, so this is ideal zero forcing case. So the problem with zero forcing arises when CZ Cz is equal to delta, which is nothing but very close to 0. That is channel gain is very small. And this can happen due to presence of noise, even if the channel gain is 0. So this makes ZF equalizer Ez, which is given as 1 over Cz, very large, which is going to boost the noise. So noise enhancement is a fundamental issue for zero forcing equalizer that is going to stay. Therefore, both these statements are actually true. First option is the correct one. Next, we proceed where we have given this circular matrix C, which we have also encountered in the first question itself in today's session, and it says that C circular matrix inverse, sorry, it should be inverse here. There are a few typos in the question. So it says the circular matrix, we have seen it can be already expressed in this format, equivalent format, where W is the IDFT matrix, gamma is the diagonal matrix with elements gamma naught to gamma m minus 1, and W is a normalized DFT matrix. It's W being Hermitian, that means W Hermitian is equal to W inverse only, and of course this C circular matrix inverse exists. So the question asks that which of the following is going to be true for the inverse of circular matrix. So let us write down the information we have. We have C circular is equal to W inverse gamma W, and we know that C circular C circular inverse exists. Oh shit. C circular inverse exists. Okay, Now see, this inverse exist is a stepping stone to compute the inverse itself, because it's like inherent assumption, right? If you are going to compute the inverse of a matrix, you first have to assume, either it's mentioned explicitly or implicitly, that the inverse exists, because otherwise if the matrix is the circular matrix is not invertible at all, there is no question of computing C circular inverse, because so that is why it is given that C circular inverse exists, so that we can proceed the compute, so that we can proceed to compute the inverse of the circular matrix. So let us write down the expression here. C circulant inverse is going to be W inverse gamma W, and we are going to use this algebraic property of this, that says ABC inverse, it is nothing but the individual inverses, but in the reverse order, A inverse. So this one we can write as follows. We start from W inverse, gamma inverse, and W inverse inverse. So double inverse, it should come into its original format, that is W, and so we get this expression. It's pretty mathematical here, like easy to solve, of course. So the second one is the correct option. Let us move to our sixth question here. You are given about the structure of diagonal matrix capital gamma here, where this C1 up to Cn corresponds to channel tap coefficients. You can also view it from OFDM perspective as the channel gain of different subcarriers. So Ci you can consider is a gain of ith channel gain of ith subcarrier. Now what would be the current implication of Ci is equal to 0? Okay, so if you briefly revisit the FDM concept, what is happening, you are dividing your wide bandwidth into small narrowband subcarriers, and each of them are carrying different symbols from transmitter to receiver. So if I make or manually, whether I set it Ci to be 0 or some channel fading occurs or Ci is very less, what does the implication of the fact that channel gain of ith subcarrier is 0? That means whatever you transmit over the particular subcarrier is not going to reach the receiver, right? Because what is happening, if you are transmitting some Si over this subcarrier Ci, then your this in time domain you can say it's a convolution, in the frequency domain it's just multiplication. So let's consider multiplication only. We are considering whatever symbol we are transmitting its frequency domain representation to be Si of Z. So you are transmitting Si of Z over this ith subcarrier Ci. So if your Ci is itself 0, what is the you received signal at receiving side? Yi is going to be just Ci times Siz, and Ci is 0, therefore Y is 0. So your receiver receives nothing. So no matter how, with what power you transmit your this symbol over ith subcarrier, if Ci is 0, inherently the channel gain is 0, your receiver is not going to receive anything. So whatever you are transmit from that point of view is lost. So therefore, let me write it down here. If Ci is equal to 0, whatever symbol being transmitted over ith subchannel is lost. Therefore, receiver receive no signal over this particular subcarrier. So therefore you have seen that no signal at receiver for this particular subcarrier, subchannel, however you want to say. So you should not stop here, because you can see the fourth option says both 1 and 2 can be correct. So before reaching any conclusion, you should analyze the second statement, which says that ith subchannel is don't care. Now that might sound pretty confusing, that what does this imply. We understand that Ci is equal to 0 means channel gain is 0, therefore the signal are not receiving, that signal is not reaching the receiver, therefore receiver receives no signal, then it's fine, no signal at receiver sounds valid only. So what does that implicate, that when you say that ith subchannel is don't care, how we can interpret this? So if you remember from our discussion and also in lectures also, maybe 2-3 weeks back, the concept of water filling algorithm, how the water filling algorithm allocates power to different channel. If you remember, water filling algorithm actually uses a optimal value in the sense that whichever channel gain is above that value, it is going to assign power to them, and whichever subcarrier's channel gain is below that optimal value, it is going to assign zero power to it. In very crude sense, water filling algorithm is going to assign the power to the strongest channel first, and then if power is left, it will be assigned to next strongest one, and it is not going to assign any power to the weakest user. Basically, mathematically, it has a optimal level power level, sorry, not power level, an optimal value it uses as a reference, and whichever subcarrier's channel gain is below that level, it is going to assign no power at all, because it consider it to be a wastage of power, which is nothing but a resource for your transmission. So why waste this resource on a weak channel when you have a stronger channel? If the stronger channel is going to provide me a better SNR and therefore resulting achievable throughput, why should I spend this resource over a weak channel? So that's the conclusion. So if a particular subcarrier channel gain is 0, that means your optimal power algorithm, that is water filling algorithm, is not going to assign any power to it, right? Therefore, actually, if you use water filling algorithm and transmitter side is not going to assign any power at all for the subcarrier. That means no symbol is going to be transmitted over this subcarrier. So therefore ith subchannel is don't care from that point of view, that it doesn't care, because you are not assigning any power to it, na? So ith subchannel is going to behave as don't care, because ith subchannel has a channel gain of 0. The optimal power algorithm detects it and assign no powers to it. So ith subchannel, basically it's like, okay fine, don't assign me any power, I don't care. So from that point of view you have to see it. So let me write down, if water filling algorithm is implemented at transmitter side, it is going to assign 0 power to ith subchannel as Ci is equal to 0. In this poor sorry ith subchannel acts as don't care. I hope I'm able to make you understand the concept between the don't care. It might sound little weird, but if you see or view this from the perspective of water filling, that might make a little bit sense. So seventh question says the channel is known to have 10 discrete taps. So what should be the minimum length of cyclic prefix in taps? We have already seen in the previous sessions also that taps actually arises from multirate propagation. Channel having multiple taps is a result of multipath propagation. Why we say that? If you write the channel response in frequency, that is a Z transform of channel, Cz, you'll see nothing but Ck z to the power minus k, where k varies from 0 to gamma, where the 0th component corresponds to the memoryless part, which is the desired signal, and the rest of the element consist of this delayed version causing the interference. So let me write down here, C0 corresponds to desired signal, rest of them are delayed versions causing interference. So we have seen that number of channel taps is equal to starts from 0 to gamma, so it's gamma plus 1, which is given as 10. That gives gamma value is equal to 9. and this rest of them which we are calling to cause interference, they are also called inter-symbol interference, because the when I say delayed version of previous symbol is going to create interference at the current instant with the current symbol. Therefore we also see this equation that number of symbols of ISI is given as gamma is equal to 9, and we have seen the goal of the introducing the cyclic prefix is to negate the effect of this what is called inter-symbol interference. That is nothing but you are going to use the last few symbols from one block to the first elements of the next block, so that the inter-block interference is mitigated. So for that we have seen the length of cyclic prefix should be greater than or equal to number of symbols of ISI, which is inter-symbol interference. Greater than or. So therefore your minimum length, so from this we get that your length of CP should be greater than equal to 9, which is the number of symbols of ISI. So minimum length of CP is 9. So first one is the correct answer. Okay, in this question it asks that which of the following block transceiver schemes you see use symbol estimation using pseudo inverse. Okay, if you have seen the lectures, you can clearly see the block transmission with cyclic prefix actually made use of pseudo inverse. Cyclic prefix use that circulant matrix, which is a square matrix m cross m. So therefore it doesn't require pseudo inverse, it just uses C circular inverse for symbol estimation. However, for block transmission with zero padding, this one required symbol estimation using pseudo inverse, because for zero padding you will have this rectangular matrix of size n cross m, so you cannot opt the inverse of it, of course. So you are have pseudo inverse of them, because in that case you have block transmission with zero padding, you take the least square approach for symbol estimation, which uses the pseudo inverse property, which is like C Hermitian, C inverse, C Hermitian. That pseudo inverse we are going to use for the estimating the symbol that has been transmitted. So let us just briefly see the what exactly happening here. So this zero padding, we first see how it happens. You denote Sn as a vector m cross 1, which is a input data block at nth instant. You apply zero padding add mu. I am using the same notation in lecture. Add mu number of zeros to Sn to get Xn, which is a n cross 1 vector. And how do we create that? Of course, you have this Sn, and you add zeros. This is mu number of zeros you are adding. That is the zero padding procedure. Of course, you can see therefore n turns out to be n is equal to m plus m mu, and xn is the symbol, sorry, xn is the block you are going to transmit through the channel. Now we have seen the pseudo circulant matrix, the channel representation in the previous session also. Let me just briefly highlight this important parts only. C0, C1 up to C mu. Mu is that you have seen that number of symbols of ISI, or mu plus 1, C0 up to C mu, total mu plus 1 channel tap coefficients. This channel representation is a pseudo circular matrix. Pseudo circular because it's just gets shifted 1 unit. C mu comes here. C naught, C mu. We are creating a discretionary line here. We'll explain the reason in a moment. And of course, it's pseudo circulant because when this C gamma comes here, the gamma plus 1th channel tap coefficient, it doesn't come alone, it comes with a memory term, that is Z inverse. And similarly here, gamma minus 1 up to Z inverse C1. C0 here. Like this, up to here you have Z inverse of C mu. So you might consider drawing a line here also. So important thing to observe here, you have if you consider this particular section, here you have this constitute of mu rows 1 up to mu is the number of symbols of ISI, and here you have mu columns. Here you have m columns, here you have m rows, so if I take Z transform of Sn, Z transform, we get S of Z, and for similarly Xn, which is transmitted through channel, we get X of Z, correct? So at receiver side we get Rz is equal to Xz times C PCZ, pseudo circular Z. And the thing what is happening for this particular structure, we observe that Rn only, because of this zero padding, Rn is the inverse Z transform of capital RZ, depends on Sn, that is nth input data block at nth instant. So there is no interference from previous instances. So how we are, and if you see the pseudo circulant channel matrix structure, this part is our main concern here. Let me this part, our goal is to nullify the effect of this part. Let me write down here how you are reaching here. This observation from here, you can do the calculation, you can understand that that is the goal of zero padding. Zero padding negates the effect of this memory portion of channel matrix. That's the main goal of the channel. That's the main goal of zero padding. So if you do zero padding in this particular format, it is seen that you are going to negate this memory portion which are able to include the which have the capacity to include the interference from previous instance data blocks. You can prevent that via zero padding, and if you do that way, we see that Rn is going to depend on Sn only. And how that is being achieved? You see, Rn is going to be, you can say, the C low times Sn. Remember, this is a n cross 1 matrix, whereas C low is a n cross m and Sn is m cross 1. So dimension wise, this holds correct. So what is the structure of the C low matrix? Actually, you can see you have n number of equations and you have m unknowns here. So this results into a overdetermined system. And okay, let me specify the C low structure, C low matrix, otherwise it will be difficult for you to understand here. So this part of matrix here is the C low matrix, which is our concern here, which is of size n cross m. It has n rows, but it has only m columns. We are discarding this row extra columns, and that brings out the relation between the received block at nth time instant to transmitted block at nth time instant. The input data block, not the transmitted one is the xn, which is the padded version of Sn, and this represent the relation between the received transmitted block at nth instant to the input data block at nth time instant without any interference from the previous instant data blocks. And that happens because of this clever way of zero padding, which negates the effect of this problematic memory part of this channel circulant matrix, and this C low is given by this portion of matrix only. So when you multiply CPCZ with XZ, it actually translates into, since the xn last mu elements are 0, it results into equivalently the product of C low with R SZ. Let me write it in a correct manner, I guess. Okay, and this overdetermined system here, this is solved using least square approach where we obtain estimate of Sn as S hat of n as follows. Here this C Hermitian C low times C low inverse C low Hermitian R n. So this is the part of pseudo inverse. This is the pseudo inverse, and this is the your received observation vector, or you can say received data block, or received block only. So you can see the symbol estimation is performed using pseudo inverse in block transmission in zero padding. However, with cyclic prefix this doesn't arise, because cyclic prefix, that CPC, is a square matrix of m cross m. Therefore you can just take inverse of that. Whereas for here, the input output relationship, the C low is the matrix of our concern here, which is a rectangular matrix. That's where the problem arises. This is not a square matrix. So therefore, when we are solving using least square approach, as it's a overdetermined system, of course n is greater than m, so therefore we obtain this pseudo inverse term here, and this is because of structure of this C low being rectangular matrix. For cyclic prefix it comes out to be a square matrix only, so you can take inverse only. But for zero padding you cannot take inverse, of course, because it's a rectangular matrix, so you need to compute the pseudo inverse for the purpose of symbol estimation. So therefore the first option is correct. Maybe for objective type question you just need to know that block transmission with zero fading need the pseudo inverse uh, 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 pseudo inverse of this effective channel matrix for symbol estimation purpose. But this is, however, the details how things are happening underlying, so this might help in visualizing things. So the ninth question asks about the what is the frequency around which A02.11 is centered. 802.11 is a family of wireless communication standards designed by this IEEE is there, of course, but along with the Ericsson and Bell Labs, this all the big players, their joint venture, they together form this 3GPP standard, and they design this wireless standards 802.11a or 802.11g. However, the important thing is, for this question you need to know that 802.11a standard is centered around 5 gigahertz frequency. So with this I conclude today's session. We'll meet on next Tuesday for our 12th session, which is I think probably going to be the last one we are having. So yeah, thank you all.